So hello everyone, welcome to the channel. So in this video, I'm going to show you how to downscale the land cover classification dataset using machine learning approach in Google Earth Engine. So now let's get started. So downscaling a land cover classification is a vital approach to enhance the spatial resolution and accuracy of land use and land cover maps. Addressing the limitation of the coarser dataset, the high resolution land cover datasets are crucial for various applications, including urban planning, ecosystem monitoring, disaster management, and climate change impact assessment. This study demonstrated a machine learning based downscaling methodology implemented in Earth Engine, integrating a multi-source satellite dataset to refine the land cover classification. The workflow begins with the modest land cover dataset, which provides us a global coverage but at the coarser spatial resolution. So to achieve a finer granularity, the study leverages a diverse dataset including the Landsat 8 surface reflectance dataset and Sentinel-1 synthetic aperture radar imagery and global human settlement layer, and a predictor variable such as normalized difference vegetation index and normalized difference water index, and some statistical percentiles of surface reflectance are computed to enrich the feature space. The integration of this urban area data and the SAR backscattered enhances the model's capability to discriminate between the various land cover types. And using the support vector mission classifier, the study trains the model on stratified samples drawn from a region of interest defined using the HydroSHED Basin boundary. The trained model downscales the land cover classification to a higher resolution of 50 meters, addressing the need for a localized land management insights. This approach illustrates the potential of combining machine learning with Earth observation data to create a scalable, accurate, and reproducible LEOC classification. So the study suggests the importance of the data fusion and machine learning in remote sensing applications, offering a pathway for developing a high-resolution land cover maps suitable for a wide range of scientific and practical purposes. So now let us get back to Earth Engine. So to downscale the land cover classification of any study region, first we have to define a region of interest. So to define a region of interest, we're going to use a specific dataset called HydroSHED. So HydroSHED Basin level 5. So this is a dataset we're going to use to delineate our study region. So the dataset availability is from 2000 and the dataset provider is WWF. So using this specific dataset, we're going to delineate our study region. So now let me get back to Earth Engine. So first we're going to insert this HydroSHED dataset into Earth Engine. So to insert this HydroSHED dataset, we define this as a variable called HydroSHED Basin equals to feature collection WWF HydroSHED version 1 Basin high base 5. And to add this layer in the Earth Engine, we defined as map.addLayer HydroSHED Basin, and with the default visualization parameter, and output the layer name as HydroSHED Basin. So once you did that, so we're going to run this code and it's going to add this layer. So now here you can able to visualize this is the HydroSHED Basin boundaries of level 5. So using this particular basin boundary, I'm going to place the point data over the basin of my choice. So you can choose any basin of your choice according to your wish. So I'm going to specifically select this part of this basin here, which is located in New Delhi. So I'm going to place a point over this specific basin here. So to do that, first let me delete this point data. So I'm going to navigate this layer. I'm going to delete my point data. So I will show you how to place a point. So we're going to navigate this section and we're going to click this option called add a marker. I'm going to place a marker over this basin of my choice. I'm going to place a marker here. So once you place your marker, so we're going to navigate this option here, show the generated code. So I'm going to copy the latitude and longitude of the point data I have placed in this basin here. So I have copied my latitude and longitude. I'm going to close this. I'm going to place my latitude and longitude over this particular variable called study point. So once you pasted your latitude and longitude in this variable called study point. So basically we have created this particular variable to hold this set of latitude and longitude values. So for that we define variable study point equals to the latitude and longitude, and we define this variable called point geometry. So in order to create a point database based on this particular point, we're gonna select this particular basin, and we're gonna delineate this basin boundary. So for that we defined doubly dot, that is earth engine dot geometry dot point data point. So there are study point, which refers to this variable called study point. So we already discussed about we are loading the Hydroset basin to delineate our study region. Next, we're gonna select the specific study boundary, that is this particular basin. So for that we define the variable called basin boundary equals to earth engine dot feature collection WWF HydroSHEDS V1 basin high base 5, and we're gonna define our region of interest. So for that we define this variable called region of interest equals to basin boundary. So we're gonna filter based on our variable from this data set. We're gonna specifically filter this particular boundary, that is basin boundary. So for that we define basin boundary dot filter bound point geometry. So referring to our point data dot we're gonna apply a loop function here. So dot map function basin. So now based on this particular point, it's gonna select this particular basin boundary, and it's going to return basin dot simplify 3000. So we are defined to simplify the geometry to reduce the processing complexity. So for that we define this, and next to center this particular layer we define this map dot center object region of interest. So the region of interest referring to our study region. So this is our study region, and to add this layer we define map dot add layer region of interest default visualization parameter, and output the layer name as region of interest. So you can able to see from this layer section here. So once you click this, you can able to visualize the region of interest. We have managed to delineate from our Hydroset basin. So we have managed to delineate our study region from the Hydroset basin. So once you did that, for next we're gonna define the time period for our analysis. So in order to downscale our Landcover classification dataset, see we have to specify our time period. So next we have to define the time period for our analysis. So for that we define this variable called analysis start. So I'm gonna specify the time period. So with the variable analysis start equals to 2020. And the end time I'm going to specify as a variable analysis end equals to 2021. So the next step, we're going to load up a modus Landcover data for the specified time period and select the Landcover band. So let me show you the modus Landcover dataset here. So the dataset is modus Landcover type early yearly global 500 meters. So the dataset availability is from 2001 to 2023, and the dataset provider is NASA. And using this specific code, you can able to access this modus Landcover dataset, and the spatial resolution of this particular dataset is around 500 meters. So these are the following set of bands that is available in the modus Landcover data. So we're gonna specifically select this particular band, that is LC type 1. So it is annual International Geosphere Biosphere Program classification. So this particular band, and this particular band provides this following set of classes here, starting from evergreen, dominated by evergreen conifer tree. So the tree cover is greater than 60%, and we have this variety of different classes like grassland, savannas, and permanent wetlands, croplands, urban and built-up lands, and permanent snow and ice, barren, and water bodies. These are the following set of class that is available in this particular LC type 1 band in our modus dataset. I'm gonna get back to Earth Engine. So to load this modus Landcover data into Earth Engine, we're gonna define this variable called modus Landcover equals to Earth Engine dot image collection modus 061 MCD1 12Q1. This is the code you can able to access the modus Landcover dataset. And in that we're gonna select the specific band called LC type 1. So I have already shown you that particular band. So this band holds for this following set of classes. And let me get back to Earth Engine. So next we're gonna filter based on our time period. So we have already specified our start and end time, that is 2020 is our start and end is 2021. So based on that we're gonna apply dot filter date, analysis start, and analysis end. And next we define this function called dot first function. So in order to retrieve the first image from the filtered collection, filtered Modis Landcover image collection. So next we have to apply the visualization parameter for our Modis Landcover dataset. So for that we define this variable called Landcover visparam, that is visualization parameter. We are setting with a minimum value of 1 and to a maximum value of 17. So it has a total of around 17 classes, 17 Landcover classes available. So we have specified the 17 different color scheme for this Landcover classes. So next we're gonna add this Landcover data into in our Earth engine. So to do this, we define map.addLayer modus landcover.clip region of interest. So our the region of interest is of this particular study region. So this basin boundary is our region of interest, and we're gonna clip it based on our region of interest, and we define this as a visualization. So we specify this particular variable Landcover visparam, referring to this particular variable having the visualization parameter for our Landcover classes, and output the layer name as Modus Landcover 500 meter resolution. So basically what we're gonna do is we're gonna downscale this Modus Landcover dataset of 500 meter resolution to a 50 meter resolution using a set of predictor variables. For example, we're gonna use Landsat 8 image, and we're gonna use this second predictor, that is our global build-up surface. So we're gonna use this particular data also, one of the predictor. So using this set of predictors, we're gonna downscale the Landcover dataset to 50 meters. So from 500 meters to we're gonna downscale to 50 meters. So next, and now let us visualize our Modus Landcover dataset here. I'm gonna navigate to the layer section. I'm gonna turn on this Modus Landcover 500 meters. So you're going to visualize the different classes that are available here. Let me zoom into it, and now we can able to visualize it. So this is our Modus Landcover data, which has around 500 meter resolution. So you can able to see that. So now let us focus on improving the spatial resolution of this particular dataset. So next we're gonna focus on the So we're gonna use define our predictor variables in order to increase the spatial resolution of our Modus data. So one of the predicted dataset is our Landsat 8 data. So we're gonna define our first predictor. So that is our Landsat 8 dataset, and for that we define this variable called Landsat images equals to Earth engine dot image collection Landsat LC8 collection 2 tire L2. And in that we're gonna select all the Landsat 8 bands. So in order to select all the Landsat 8 bands, we define this as a dot select. SR represents the surface reflectance. So we're gonna select all the bands of Landsat 8. So to do that, we define SR B dot star. So as a result, this is gonna select all the Landsat 8 bands. And next we're gonna filter with a specific time period. So for that, we defined the dot filter date, analysis start and analysis end. So previously we have specified the start and end date for our analysis. So the analysis starts from 2020 and the analysis end at 2021. And next we're gonna filter with a specific study region, that is this particular basin. So this is our region of interest. So in order to filter based on our study region, we define dot filter bound region of interest. So the region of interest which represents our study region. And next we're gonna filter with a satellite image with the least cloud contaminated image. So to do that, we define dot filter earth engine dot filter less than, so cloud cover equals to, that is less than cloud cover less than 10%. And next we're gonna create a loop function. So for that we define dot map function image, referring to our Landsat 8 image. So we're gonna apply the gain and offset adjustment for the surface reflectance in the Landsat 8 image. So you can able to visualize the band section of Landsat 8 image. So we have this offset, and so you can able to see the scale and offset here. So we have applied this coefficient in our Landsat 8 image before further analysis. So in order to apply this gain and offset here, that is our scale and offset. So we're gonna multiply the scale value, and we're gonna add our offset value to our Landsat 8 image. So to do that, we defined a variable called gain equals to earth engine dot number. So for the number format, we are using this specific number function, and we are accessing the image, and In that we are referring to a reflectance multiband 1, which refers to a scale value, and next is a reflectance add band 1, which referring to our offset value. So we define the variable for gain equals to earth_number image.get reflectance multiband, which represents our scale value. And next, our offset value, we define the variable called offset equals to earth_number image.get reflectance add band, which represents our scale, that is our offset value. So this is our offset value. And to apply this coefficient to our image, we define a variable called corrected image equals to image dot multiplying the gain value and adding the offset value to our Landsat 8 image. So once you applied this corrections, that is our scaling values, we have to next we're gonna proceed towards creating the normalized difference vegetation index and the normalized difference water index from our Landsat 8 image. So to do that, we define a variable called ndvi equals to the corrected image dot normalized difference. So it's going to apply the formula, that is SR B5 minus B4 divided by B5 plus B4. So specifying normalized difference is going to give the formula, that is B5 minus B4 divided by B5 plus B4. So it's going to generate our ndvi, that is normalized difference vegetation index, and we're going to rename as ndvi. And next, to generate our ndwi, that is normalized difference water index, we defined equals to the corrected image, referring to this particular image where we have applied our scaling factor, and dot normalized difference. So we're going to apply to create a normalized different water index. We're going to use the specific formula, that is B3 minus B5 divided by B3 plus B5. So and we're going to rename as ndwi, normalized difference water index. And so next we're going to define this variable called shortwave infrared band equals to the corrected image. So the Landsat 8 image contains the shortwave infrared band. So we're going to access by the corrected image variable we have specified here after applying the scaling factor. And in that we're going to select this shortwave infrared band, so 6 and 7, which represents the shortwave infrared band in Landsat 8 image. So these are the SR-B6 and SR-B7, which represents the shortwave infrared band, which is available in Landsat 8 image. So this particular band is very useful in case of detecting the urban areas and the moisture content, and also vegetation moisture content. So we're gonna use this particular band here. So next we're gonna return the image that is earth_image cat function. So in order to create an image stack, so we are using this function called stack function, and in that we're going to use this set of ndvi and ndwi and the shortwave infrared bands. So now in order to view the details of this particular image, we're going to visualize it in our console section here. So I'm going to mention it as print, and I'm going to copy this Landsat image, and I'm going to paste it here. And we're going to run this and visualize it in our console section here. So now in the console section, you can able to visualize it. That is our image collection, Landsat LC8 collection 2 tier 1. So in the features, I'm going to click this down arrow button. So we can able to see there is a lot of image that is available. So I'm going to click the first image. So in the bands, we have this following set of bands, that is ndvi, ndwi, SR-B6 and SR-B7, which these two bands represent the shortwave infrared bands of Landsat 8 image. So these bands will act as our first set of predictors in order to downscale our Landcover image. So in the next step, we're going to calculate the statistical percentile for the Landsat predictor variable. So that is, I want to use some sort of statistical operations such as the percentile to reflect the ndvi and other band changes during a time. For example, instead of having a collection, the collection of all ndvi data that makes your code more, it takes a more processing time. So to avoid that, we can use some sort of statistical operations to produce a limited number of images that's reflecting the indices changes during the time. So for example, the statistical percentile is very useful in this regard. So to do that, we can define this variable called Landsat stats equals to. So we're gonna get the Landsat image, that is Landsat images, and we're gonna apply the reducer function, and we're gonna define Earth Engine dot reducer dot percentile. So it is very useful technique to show the temporal changes based on the different thresholds in our data. So instead of having all the data during the time span, you can use the percentile to show the temporal variations with a limited number of images. So I'm gonna give it as 25, 50, and 75. So what does this mean? So here the percentile 50, which referring to those of values in a pixel in which 50%, the 50% of the observation which lies before that. So for example, the percentile 50, which selects the NDVI value, that select 50% of the whole of the NDVI value. So the 50% of the whole NDVI value, or less than that single value. And in case of the 75 percentile, so the percentile here, it is to calculating for all input bands. It includes the NDVI, NDWI, and shortwave infrared. So that's reflecting the changes of these variable during a time. So for example, in the console section, you can able to see we have a total of around 120 images starting from 0, or starting from 1 to 119 images. We have a total of 119 images. So for each image we have around 4 bands. So totally we have around 119 images, and each image has 4 bands. So you can able to see we have NDVI, NDWI, SR B6, and SR B7, and we are having a total of 476 bands. So I want to limit the few number of Landsat data to reflect the temporal changes, and this specific technique is very helpful. This specific technique is very helpful to make a light dataset which highly reduces the processing time. So previously we had around 119 images. So now let's visualize it after applying these changes here. After applying this percentile function, so we're gonna print, and we're gonna visualize the result. So we're gonna copy this Landsat stats and paste it inside this print function, and we're gonna run this code, and let us visualize the result now. So in the console section, you can able to see here. So we have managed to reduce the number of bands here. So currently it is around only 12 bands. So you can able to visualize it. So after applying this percentile function, we have managed to reduce the number of images. So now in the next step, we're gonna add our second predictor. That is our to add our urban area data as a predictor. So this will be our second predictor. So let us visualize the details about this particular dataset here. So this particular data is a global build-up surface. So the dataset availability is from 1975 to 2030, and the dataset provider is GC ECJRC. So using this specific code, you can able to access this particular dataset, and we're gonna see the description. So this raster dataset depicts the distribution of built-up surface expressed in square meter per centimeter per 100 meter grid cell. So the dataset measures the total build-up surface, and the build-up surface allocated to each cell of predominant non-residential uses. The data is spatially temporally interpolated and extrapolated from 1975 to 2030 in 5 years interval. So you can go through this data and the bands that is available. So it has a resolution of around 100 meters, and we have 2 bands. One is built surface, and the second one is the built surface N res, that is N residential, and units in meter square, and description is build-up surface per grid cell and non-residential build-up surface per grid cells. So in this dataset, we're gonna specifically use this particular band called build surface. So the build-up surface per grid cell, so units is meter square. So we're gonna use this specific band. So this particular dataset is very useful in our downscaling the land use land cover classification, because this particular dataset provides us an urban area. So in this way, you can differentiate between the urban and non-urban areas. So to add this data, we're going to define a variable called urban layer 2020 equals to earth engine dot image jrc ghsl, and we're going to specify this code to access this particular dataset. And in that, we're going to select the specific band called build surface. So next, we're going to define the visualization parameter for this particular dataset. So to do that, we're going to define this variable called urban vis params that represents the urban visualization parameter, and we are setting a minimum value of 0 and to a maximum of 8000. And the color palettes, we're going to use this following color palettes to differentiate between the non-urban areas and urban areas. And to add this layer in Earth Engine, we defined map.add layer urban layer 2020 representing this variable. We're going to clip our region of interest. So this is our region of interest, and this is our region of interest. So this is our region of interest, and we're going to specify this visualization parameter, that is urban vis param, representing this variable for visualization, and output the layer name as urban area 2020. So now to visualize this layer, we're going to navigate to this option here, layer section, and in that we're going to click this option called urban area 2020. So it's going to pop up here. So let us visualize it. So now we can able to see from this image here, all the urban areas are being clearly highlighted in white color. You can able to visualize it. So it is located, this particular urban areas is located in New Delhi. So you can able to see that all the white areas which indicates the urban area, and the black which represents the non-urban areas. For example, I'm going to zoom to this part of the areas here. So I'm going to turn to a satellite mode. You can clearly visualize the result. I'm going to turn this off. So you can able to see that this is an urban area. So next, we're gonna further proceed to analysis. We're gonna add our third predictor, that is our Sentinel SAR image, Sentinel-1 SAR Imagery. So to load a Sentinel-1 SAR Imagery, we defined as variable SAR image equals to image collection Copernicus S1 GRD. So now let me explain about this particular dataset here. So synthetic aperture radar, that is Sentinel-1 SAR. So it is of 10 meter resolution, and the dataset provided is European Union and ESA Copernicus, and the code dataset can be accessed through this particular code. And these are the following bands that is available in Sentinel-1 SAR Imagery. So HH, which represents the single copolarization, horizontal transmit and horizontal receive, and VHV is a dual band cross polarization, horizontal transmit and vertical receive, and VV is a single copolarization, vertical transmit and vertical receive, and last VH, which represents the dual band cross polarization, vertical transmit and horizontal receive. So now let me get back to the Earth Engine. So next we're going to filter with a specific timeline. So we have already given in the analysis start and analysis end, that is 2020 and 2021, and we're going to filter with a specific study region, that is our study area, that is our basin. This is our study region. Now we can able to see that. So based on this particular study region, we're going to filter. So for that we define dot filter bound region of interest. And next we're going to filter with the specific we're going to filter with by its polarization. So for that we define dot filter earth engine dot filter dot list contain the transmitter receiver polarization VV. And next we're going to filter by we're gonna filter by its instrument mode. So for that we define dot filter, dot filter dot equals instrument mode is IW. So the IW, which represents, let me show you that. So the IW is the interferometric wide swath mode. It is one of the primary operation modes of Sentinel-1 synthetic aperture radar instrument, which is used for the wide range of Earth observation application. So this mode is specifically designed to capture the high resolution imagery over a wide area, making it suitable for applications such as land monitoring and oceanography and disaster response. Specifically, this is useful to capture the image at wide range of Earth observation. So next we're gonna filter it by the orbit direction. So to filter it by orbit direction, we define dot filter earth engine dot filter equal orbit property pass is descending. So in case of descending, the satellite moves from north to south. So in case of ascending, the satellite moves from south to north. But in case of descending, the satellite moves from north to south. So next we're gonna select it by the specific band called we're gonna select it by VV band. So which represents VV, which represents a single copolarization, vertical transmitted and vertical receive. So the short description about the VV polarization. So in VV polarization, the radar transmits vertically polarized waves and receiver also detects the vertically polarized components of the backscattered wave. And this means the both transmitted and received signals are vertically polarized. So in an image, areas with the high VV backscattered appears brighter, indicating the surface that are rough or have a lot of vertical structures. So conversely, if a low VV backscattered appears darker, typically indicating a smoother surface or open water. So last we applied as a mean function in order to calculate the mean of the SAR image. So for that we applied as a mean function. So in the next step, we're gonna prepare the dataset by combining all the predictor layers such as the Landsat 8 dataset, urban data, SAR and MODIS dataset. So to do that, we define this variable called predictor dataset equals to the Landsat stat dot add band. So we're gonna add urban layer 2020 and we're gonna add MODIS Landcover, and last we're gonna add SAR image. So once you combined all the predictor layers, we can next proceed towards creating a training dataset using stratified sampling. So to do that, we define this variable called training samples equals to the predictor dataset referring to this particular variable dot stratified sample. So the stratified sample is an automatic method for sampling from each classes. So for example, we have this target variable we have. For example, we want to do sampling for the sampling for different land covers we have in LC type 1. So the stratified sample do this process automatically, and also you don't need to do this process manually, and it's very helpful. So here the first which represents a number of points. So for example, I could like to collect 100 points for each class separately. So next is the class band. So the class band, the band I want to collect sample based on the region, that is the LC type 1, and the region of interest is our study region, that is this particular basin. And the spatial resolution, I'm gonna provide it as 100 meters of resolution, and also the spatial resolution can range between 30 to 100. For example, the Landsat band has a 30-meter resolution, and the global build-up dataset has a spatial resolution of 100. So the spatial resolution can range between 30 to 100. So I'm gonna specify as a 100-meter resolution. So once you created our training dataset here, so we're gonna focus on train our machine learning model SVM on the training dataset. So to do that, we define this variable called Landcover classifier equals to earthengine.classify. So I have specified the lib SVM as that is our model. So next we define .train and features will be training samples referring to our training dataset here. referring to this variable called training samples, and the class property refers to our LC type 1 Landcover band, and the input properties will be our predictor dataset containing all the different predictor datasets starting from our Landsat imagery, and the global urban build-up dataset, and SAR imagery, and our modus dataset. And last, we define dot band names. Suppose if you want to get the names from your dataset, you have to specify as a dot band names function. So next, we're going to classify our land cover at high resolution using our trained model. So to classify the land cover at high resolution using our trained model, first we define this variable called the predictor bands equals to the predictor dataset and dot band names function and dot remove LC type 1. So I can able to see that now I'm going to remove this the LC type 1 one from the predictor, because the predictor must be used for the modeling processes from now on, and also the LC type must be removed from here. So for that we have we're gonna remove the LC type 1. So next we're gonna define a variable called high resolution land cover and equals to the predictor dataset dot select the predictor bands, referring to this particular variable predictor bands, and dot classify the land cover classifier, which is referring to our model here, so you can able to see this variable. So next, to display this high resolution land cover classification, we define map.addLayer high resolution land cover dot clip a region of interest referring to our study region, and a visualization parameter, the land covers param we have previously defined for visualization purposes, and output the layer as high resolution land cover of 50 meter of resolution. So to visualize the details of this particular image, we define as a print high resolution land cover. So now let us visualize the result here. So we're going to navigate this option called run, and we're going to click run. So to visualize the details of this specific image, let me turn off this HydroSHED Basin. So I'm going to turn on the high resolution land cover dataset. So in the console section, it's currently computing our details about this high resolution land cover. So now it's loading here. Let me zoom into this land cover dataset. So finally the image is ready here in the console section here. So you can able to visualize we have bands. It lists only one element. So that is our classification sign int EPSG. So this is the details about the specific image here. So now let us take a look at the high resolution LULC image. And now here you can able to visualize the modus land cover high resolution modus land cover dataset here. So let me so you can able to see that this is the high resolution land cover dataset, and this is the modus land cover of 500 meter resolution. And you can see that this is the modus land cover of 500 meter resolution. So now we have downscaled, and we have made the resolution to around 50 meters using our machine learning technique here. I'm going to click this high resolution land cover dataset, so you can compare the difference here. So you're going to turn off, I have turned off the high resolution, so now we're going to turn on. So now we can able to visualize it. Let me go to the satellite mode here. You can compare the difference. So now we are currently visualizing the high resolution land cover dataset. So I can able to see the difference in that. So we have managed to downscale the modus 500 meter resolution to 50 meter resolution using our machine learning technique in Google Earth Engine. So let me get back here. So next we're going to focus on exporting this high resolution land cover classification dataset to a Google Drive. So to do that, we defined as an export.image.dry. So with the image section, we're going to define as high resolution land cover .clip region of interest. So the region of interest, which refers to our study region, and the description is we're going to give it as a high resolution land cover dataset, and the spatial resolution, it is around 50 meters. So we have managed to reduce from 500 meters to 50 meter of resolution using our machine learning approach, which is available in Earth Engine. So particularly we have used this SVM model, so to do that. And next we're going to define the region as region of interest, and CRS is our coordinate reference system, is of EPSG 4326 is a projection, and max pixel level we given, and the folder we're going to give it as land cover classification. So now we're going to navigate to this option called task section, and in that there is an unsubmitted task called high resolution land cover, and we're going to click this option called run in order to initiate this image export. I'm going to click run. So now the new window pop up saying initiate image export, and the task is of a high resolution land cover dataset, and the spatial resolution is around 50 meters. So you can export this particular high resolution image to your drive or the cloud storage or our Earth Engine asset. So we're gonna export to a Google Drive, our drive. So I've selected my drive, and the drive folder is land cover classification. File name is high resolution land cover. So you can mention your time, or you can mention the year of your choice here, and the file format is GeoTIFF. So now to export this image, we will click this option called run. So in this video, we have focused on downscaling our land cover classification dataset using machine learning approach in Google Earth Engine, and the code link will be given in the description section of this video. So thanks for watching, and make sure that you subscribe to our channel and give us a like.